you are a champion if you have made it this far to talk about the log model. And you think this is going to be the hardest one, but just wait till we simplify it. It's actually not as bad as you think. So here I've got log base e on y and log base e on x. In other words, as server speed increases by some multiplicative effect, there is a multiplicative effect on y. And I especially chose to use the same base. I actually paused the video and thought for a while, should I show you what happens if you use different bases? And the math is a little nastier, and I decided, no, let's just not do that. So let's have both of these be to the same base so that it simplifies nicely. You might think to yourself, because it's log x and log y, that means it's just an x on y relationship. And sometimes these kind of models can look like that, except there's an explosion of the data in some direction, and using logs helps bring it in, as well as helps the theoretical that it should be some multiplicative effect. And there's a lot more variety of types of curvature, subtle one way or another, that this model allows. So let's see if we can simplify this. The first thing I'm going to do is get rid of the log, so I just have y, by using this trick, which is what we did in the last video, and then splitting the exponent. And now I'm going to use the trick of logs from right here, where if I have some number times a log, I can put that inside as an exponent on the x, which probably looks like I've made this thing look even uglier than ever. But I can use this rule right here to simplify it so that this becomes a function of y with x raised to an exponent. And I think if I stand in just the right spot, I can give you shade so you can see from the sun shining through my window, there's no more logs. They all went away. In fact, the only time that that base shows up is here of the base times this exponent. What's really happening when we look at a slope value here is we're saying, what should the exponent on x be? And here, y should equal almost x squared, not quite x squared. When I say there's a lot of variety that can go on here, that's what I'm talking about. We could model y equals x squared or x cubed or x to the fourth, and we'll let the data decide for us. It should be x to what power? And not only does that give us variety in the types of curves we can talk about, but also remember back in the day when we were making data, we had y equals our intercept plus the slope times x plus some residual. And if you recall, if we didn't add a residual, then all our data points went in a nice straight line. But once we used the residual, then we had some spread around our regression line. Well, we added residuals. But in this case, if we follow what happens to that residual, it becomes that we have our base raised to the power of those residuals. So the residuals also have a multiplicative effect. What that means is, as y goes up, the residuals spread out. So this allows us to have some non-constant variance anytime we're doing a log y. So it's also true of the model that we did in the last video. We can model some things that have a horn shape. It doesn't take care of all types of situations when this happens. In fact, in the final project, I'll tell you there are some examples of where you have that fan shape and you can get rid of it by doing the right log. It also has some where you can't get rid of it and you just have to learn to deal with it. But there's lots of reasons why, even though it looks like we're just doing an XY type model, we get a lot of variety by doing log X, log Y. So I want to take this piece right here and I'm going to slide it up. That way we can see what happens as we increase X. Now for our classic linear model, we add something to X and it adds something to Y. As you might guess, because we've logged both, we're going to multiply something by X and get a multiply effect on Y. But if you wanted to try adding, then you would take X plus 1 raised to the 1.59 power, and you would have to simplify that and go look up the binomial theorem. This is not pretty. It's not going to end well. We don't want to try adding to X. Instead, we're going to multiply X, and in this case, I've chosen 1.05. Where did that 1.05 come from? It's a 5% addition to X, because I want to have a sentence that says, if X increases by 5%, then, well, let's figure out what happens. I'm going to simplify this by breaking out that exponent, and then if I move this guy to the front, then you can see if I stand just right so that I'm blocking the sun for you, which, doggone it, that's impossible. Oh, wait, right there, sweet spot, I'm blocking all the sunlight. So this is what we had before, right, the E and the X that we had at the beginning, plus this extra piece, that 1.05 that we multiplied by the x, raised to the power of this beta 1. And that is a number which I can simplify in my calculator, but if I do, I'll have to move, and then I'll never find that sweet spot to block all that sun. It turns out to be 1.1, which is why I picked that particular beta, because I thought it gave us nice numbers. But that 1.1 means we're multiplying what we had before by 100% plus 10% more. So if x increases by 5%, then y increases by 10%. So in the context of this scenario, that would say if our server speeds up by 5%, then we expect 10% more users playing X-Men Online, which I don't know if that game actually exists. I just feel like it probably should and would be cool. But that's a sentence that a client can work with. I see. So the server speed, if we can get this much more, how much more? Well, it depends on how fast it already is. The faster it goes, the harder it is to get a 5% increase. But that also means the more players we have, a 10% increase could mean a lot. If you only have a few players, then a 10% increase means less. So that's the relationship between them that you can play with. Let's go to the bottom line, because I know for a lot of you, it's really the bottom line is what you care about, and you probably skipped through the rest of the video. Shame on you, because I've worked really hard all video long to block these sunlight streaks on my board. But here's the idea. You have log y and log x. Notice they have the same base, a, whatever it is, e or 10, I don't care. But that means that if x increases by some p%, then don't forget that, like, if you say 3%, that needs to be 0.03. That's why it's divided by 100. So you would use 1.03 raised to the slope power. And then whatever number you get from there, you subtract from 1. So if you got 1.07, you would subtract from 1 to give you 0.07, which would be 7%. That's why it's times 100 to get it back into the 7%. But this equation might look nasty. It's not that bad, especially if you don't get yourself confused on those percentage points, right? It's 1 minus p if p already was a percentage, 1 raised to the beta 1, and then 1 minus that as your percentage. But there's all the different types of log models. Instead of just saying as x increases or y increases, we talk about percentages wherever they're logged. But in the next video, let's try to put all of it together so that we can keep track of it, and that's probably the video you'll want to use as reference.